Welcome to Brain Vision.
In the first item, we have to calculate the value of the ground state energy of an oxygen molecule. We begin by calculating the value of E1, which is what we have to calculate. E1 is equals to 1 squared, which is equals to 1 times H squared divided by 8 times the mass of that molecule times L squared. We already know what is H, we know what is L, so the only thing that we have to calculate before evaluating the ground state energy is the mass of the oxygen molecule. And we can use the periodic table of elements to recover some information about the oxygen atom. And each atom of oxygen has approximately 16 mu units of mass. Then it's easy to see that the mass of the oxygen molecule that has 2 oxygen atoms is equals to 32 mu. Finally, the ground state energy is equals to H squared, so 6.63 times 10 to minus 34 squared divided by 8 times 32 times 1.66 times 10 to minus 27, which is the constant mu, converting from units of atomic mass to kilograms, and this multiplies L squared, which is equals to 4 millimeters. So, because of that milli, there is a 10 to the minus 3 factor. This will result in an energy that is measured in joules. In order to make it more suitable for the situation, we convert that energy from joules to electron volts, and we do so by dividing the energy by the electron charge, which is 1.6 times 10 to minus 19. Finally, the energy of the ground state is approximately 4 times 10 to minus 19 electron volts. In the second item, we have a different situation. In the second item, we are given the energy and we have to determine what is the quantum number. But it's not an ordinary energy, it's the average thermal energy. That average thermal energy is equals to 1/2 of K times T. And then the problem says that the temperature is equals to 300 kelvins. Now we have to calculate what is this average thermal energy. It's very easy to see that 300 divided by 2 is equals to 150. So we have the thermal energy being equals to 150 times the Boltzmann's constant. I will put a subscript B in the Boltzmann constant so we don't make a confusion between the Boltzmann constant and the Kelvin unit. Then we have to calculate what is the quantum number of that energy state. So to do that, we equate that average thermal energy with the equation for the energy. And this gives us the following. 150 Boltzmann constant is equals to m squared h squared divided by 8m L squared. Solving for n, we get the following. 150 Boltzmann constant times 8 times m times L squared divided by h squared is equals to n. And then we have the square root of everything here. Now, as the next step, what we have to do is simplify that square root, and we can do so as follows. The square root of L squared is equals to L, and the square root of h squared is equals to n. So we are left with the square root of 150 Boltzmann constant times 8 times m times L divided by h, and this is equals to n. Now, all we have to do is plug in the values and get the value of n. Then, n is equals to the square root of 150 times 8 times m. We had already seen that m is approximately 32 times mu, and mu is approximately 1.66 times 10 to minus 27, and this is multiplied by Boltzmann's constant, which is 1.38 times 10 to the minus 23. Then we have L, which is equals to 4 millimeters, so 4 times 10 to the minus 3, and dividing all this is Planck's constant, which is approximately 6.63 times 10 to minus 34, and this results in a quantum number of approximately 2 times 10 to the 8. On the next item, we have to calculate what is the energy gap between two neighboring states. So we have to calculate what is delta, which is given by En plus 1 minus En. By using the expression for En, we have the following: n plus 1 squared minus m squared, and there is a common factor of h squared divided by 8m L squared. And this is equals to n squared plus 1 plus 2n minus n squared times U1. This factor is equals to U1. So this is a simple calculation. This is equals to, well, the n squared and the minus n squared factors cancel out, and we have 2n plus 1 times U1. But if we have very large quantum numbers, then we can approximate 2n plus 1 to 2n. Therefore, the energy gap is equals to 2n times U1. We had already evaluated what is U1. So, to remember, 4 times 10 to minus 19. So we have that the energy gap is approximately 2 times n times 4 times 10 to minus 19 electron volts. And this is finally equals to 2 times 4 times n, which is equals to 2 times 10 to the 8th, times 10 to minus 19. And this is equals to 16 times 10 to minus 11, which is equals to 1.6 times 10 to minus 10. And finally, our answer is that the energy gap is approximately 10 to the minus 10 electron volts.